Hi everyone, so this is going to be the first video in a little course I'm doing called Quantum Mechanics for High Schoolers. So the purpose of this course is going to be to allow really an entry point for people to get into quantum mechanics between the more intuitive stuff that you'd find on like YouTube channels like Kurzgesagt or like a Neil deGrasse Tyson podcast and like actual textbooks with a bunch of math in it. So, I'm in high school and I kind of had to brute force through Griffiths' Introduction to Quantum Mechanics. It's a textbook to try to learn the subject for myself. And that was only after a very long period of me kind of feeling frustrated in that I would have these very intuitive explanations that I could find on YouTube that I could easily understand, but never really gave me the depth that I wanted. And then if I ever tried to go beyond that, I would be immediately hit with this, this crazy math that's years beyond my formal education as a high schooler. So I've always been looking for sources that are kind of like to bridge the gap between that intuitive, very basic understanding and the heavy mathematics that you find in actual professional physics, so that people like me who are hobbyists and who are really passionate about the subject and are a little impatient to wait for their formal education in college and whatnot to really get into the subject. So what I'm going to do here is I'm going to try to give you an understanding of the math behind quantum mechanics and understand what the equations mean and even how to set up quantum mechanical problems without necessarily giving you the ability to do that math. And that's not too much of a problem because now we have calculators like Wolfram Alpha. You can plug in an integral and you'll get out a lot of the time a good response. So you really be able to understand how the math behind quantum mechanics works and even how it gives rise to a lot of these strange quantum properties in this course. So to do this course, I think you need to have a pretty strong grasp of just basic calculus, so just integrals and derivatives, what they are, what they mean, infinite summation and slopes and all that stuff. The basics of complex numbers would help as well, like complex conjugates and just what the imaginary number is, what it means, square root of -1. And that intuitive explanation of quantum mechanics I mentioned before, though that's not necessarily required for this. It's just, it would help out. All right, so my first chapter is going to be the wave function and normalization. So this right here is the wave function. It's given by the Greek letter psi, and with one particle in one dimension, you're going to have the parameters x and t, as you can see here. And when you plug in some sort of position and some sort of time, you're going to get a value. Now, this value has absolutely no physical significance because it's usually going to be a complex number. So when you plug in a coordinate and a time into the wave function, you're going to get out some number that's going to include I in it. And when a number has that square root of -1 in it, that means it can't have any sort of physical significance because it's not a real number. It's an imaginary number. And even if you take out the real component, that doesn't mean anything. So now you might be asking, well, people hype up this wave function a lot. It's what describes the quantum system, people say. So how can that be true if the output of a wave function has no physical significance? Well, that's because the wave function in its base state is kind of like a sheathed Swiss Army knife. And you really have to poke at it and prod at it and manipulate it to get information out of it. But once you do that, you can get literally any information about the quantum system you want out of just this one function. So it's very useful. So like the basic form of manipulation, for example, in a wave function, or for a wave function to give you information about the system, is by multiplying it by its complex conjugate. So this asterisk up here, this signifies the complex conjugate. When you multiply a wave function by its complex conjugate, you get what's called the magnitude squared of the wave function. And that signifies the probability. So if you plug a coordinate and a time into the magnitude squared of a wave function, or if you multiply a wave function with the value of a wave function at a certain coordinate at a certain time by its complex conjugate at the same coordinate and time, you will get the probability of the particle being in that position at that time. So that's a relatively simple way to get information out of the wave function as is, and that's going to be the basis for all the other ways you can manipulate the wave function to get whatever information you want. So if we're taking an example of a wave function, this right here is a normal distribution wave function. So if you want to visualize the graph without that imaginary component right here, which makes it ungraphable, it's going to be like a little hump right in the right centered around the origin, centered around x equals 0, and it's going to just be a little bit up above the x-axis, and then it's going to come back down like a little hill. And this constant a here we'll talk about in a little bit. So if I want to multiply this wave function by its complex conjugate, psi star, you're going to see basically the same exact equation, except these two e's are going to be different. Because if you multiply, because the point of a complex conjugate is when you multiply a complex conjugate by the normal number or the normal function or whatever, you're going to cancel out the two negative parts, and you're going to get in return solely a real number or a real function or whatever it's going to be, something without an I. So if you multiply these two functions together, when you multiply two exponentials together, the exponents are going to add together. So you're going to get e to the it minus it, so e to the 0. So these e's are both going to cancel out. And you're going to get just this, which is a completely real function. There's no imaginary numbers at all involved. And so therefore, it actually can mean something. And what it means is probability we found through experimental data. Now, what is this a here? So this a is what's called the normalization constant. So if you think about what this magnitude squared means, it's the probability of the particle being observed at a position x at time t, right? So logically then, you would have this necessary condition that if you were to look over all of space and sum up all the probabilities, so all the x's, look at all the x's and say, what's the probability of the particle being here, probability here, probability here, probability here. If you were to sum up all of those probabilities, all those different x's from x equals negative infinity to x equals infinity, you should get out 1. So if you take the integral, in other words, if you take the integral of the magnitude squared from negative infinity to infinity with respect to x, you should get out 1 because the particle has to exist somewhere. Like, for example, if you were to get 0.9 from this integral, then that means there's a 90% chance the particle does exist somewhere in real space, but there's a 10% chance that the particle, if you observe the wave function and collapse it into an actual, like, if you measure the wave function and try to get out a value for the position, there's a 10% chance that it just doesn't exist at all. And that's not how things work, at least on this scale of physics. Things aren't just constantly blipping in and out of existence like that. And if they did, they would at least leave some sort of mark that can be mathematically modeled. So the probability of the particle existing somewhere has to be 1, has to be 100%. But this isn't true for every single wave function you're going to find. Not every wave function you're going to find is going to be able to be multiplied by its complex conjugate and immediately get 1 if you take that integral. So the way you do that, the way you make sure that this condition is satisfied is by multiplying the wave function by what's called the normalization constant, or a. So in order to satisfy this condition, you're going to introduce this constant a here, such that if you were to take the integral from negative infinity to infinity across all space of the wave function multiplied by a times its complex conjugate multiplied by a. In other words, a squared times the magnitude squared of the wave function, it's going to equal 1. So if this doesn't equal 1, then you're going to have this constant right here that's going to be multiplied by this that's going to make it 1. So if we go back to the example wave function we had before, and you you take the integral from negative infinity to infinity over all real space of the magnitude squared, which is right here as I showed you before, and you multiply that by a, then you should be able to find a such that this whole expression equals 1, right? So if you were to solve that, if you were to divide both sides by a squared, right, and that's going to cancel, and then you divide both sides by a squared, what you're going to get, and you solve this integral right here using just a basic integral calculator. You could just look one up and plug this in and you'll find it, and you'll get the answer. You're going to get out this. So 1 over 2 times rad pi equals 1 over a squared. And then through simple algebra, you'll be able to find that a equals the square root of 2 times the square root of pi, all inside that big square root right there. So then, now that you have a, you can plug that into the initial wave function that's not multiplied by its complex conjugate yet to get the total complete wave function completely. It's called the normalized wave function. So if you plug in this, what happens is the 2's are going to cancel out, and you're going to have these the rad pi cancel with the rad pi on the bottom, and you're going to get psi of x of t equals 1 over the cube root of pi times e to the negative x squared over 2 times e to the it. And that's going to be your final wave function. And just to show you what that looks like, this right here is the magnitude squared of the wave function graphed on a plot. As you can see, the t is changing over here over time, and because these terms have the imaginary number in them and they cancel out, this wave function is going to be completely independent of time. So the probability distribution of the particle, the likelihood of the particle being in any given place, is not changing throughout time because these time terms are canceling out with each other to make the probability distribution. You can see y here, this is the original wave function, y2 is the complex conjugate, and y is the magnitude squared, or the probability distribution. All right, so that's all I got for this one. Thank you very much.